It's my pleasure to introduce Professor Ganguli. Professor Ashok Kumar Ganguli obtained his PhD degree from the Solid State and Structural Chemistry Unit of Indian Institute of Science, Bangalore in 1990 in the area of thallium-based high-temperature superconductors, for which he got the Sudborough Ed Medal. He has been a visiting scientist at DuPont Company, USA, and a postdoctoral associate and visiting scientist at Ames Laboratory, Iowa State University. His interests are in the synthesis and properties of materials, dielectric and superconducting oxides, quaternary chalcogenides, polar intermetallics, and nanocrystalline materials, nanoparticles, nanorods, and nanocomposites. Dr. Ganguli is the recipient of the MRSI Medal for 2006 for his contributions to material science. He has also been awarded the CRSI Medal for 2007 for his contributions to chemistry. Dr. Ganguli has coordinated several national and international meetings on materials and nanotechnology. He has given several invited lectures in India and abroad on various aspects of the design of novel solids and synthesis of nanocrystalline materials. He has published around 100 papers in refereed journals. He is also a collaborating partner of the MHRD Quantum Nanosystems Virtual Center project from IIT Delhi. I welcome Professor.
I'm very glad to be here. This is my second visit to this institute, and it's going to be a very different talk from what you have been listening so far, I think. The idea of my talk would be, people are talking about quantum computers and DNA computers, and but my idea is just miniaturizing the existing what you call components of normal computers. So basically to reduce the size of the chips. So how do you reduce the size of the chips? So you reduce the components like the interconnects by making nanoparticles, trying to assemble them, trying to make wires out of them, etc. So it's mostly going to be a chemistry type of talk, and so you'll have to bear with me with that. So this is for students, all of you. So for students, you know what are nanomaterials and why nanomaterials are important, because when you go from the micron size to the nanometer size, you go into a regime of quantum phenomena, so classical physics doesn't hold. What are the major effects you see are changes in the electronic properties, especially quantum size effects, single electron tunneling, reversal of magnetization. If you are a material scientist, you know you have changes in the microstructure, the melting point reduces, the ductility changes, the hardness changes, and from the activity point of view, your structure can change, your catalytic properties certainly gets enhanced. The surfaces and interfaces become important because the size of the particles are so small that there are hardly any particles in the bulk. So this is just one example. This, you know, for catalysis, you have small size particles, so surface number of particles on the surface increases. If you have domains which have dipoles, as you are reducing the size of the particle, the ordered dipoles gets reduced, and so you get more disordered dipoles. So basically, if you have a ferroelectric material and you reduce the size, you will go to a paraelectric regime. If you have a ferromagnetic material, you will get paramagnetism. Or in other words, you may get a reversal of the magnetization. But the idea is to tell you how, as chemists, you can control the size and shape of these particles. Normally, you make materials either by physical techniques like plasma synthesis or laser ablation or electron beam lithography, etc. What I would be discussing is chemical methods. And there are several chemical methods people use like, very common methods are solvothermal, hydrothermal, and microemulsion method. Most of the time, these methods are called soft chemistry because you use much lower temperatures. If you use an electron beam, the local temperatures will be very high, all right, and you can cause changes in the structure of the material. These work at much lower temperatures. So this is called soft chemistry or chimie douce in French. And I would be talking to you about microemulsions, which is one technique. So I'll try to show you some methodologies by which you can control the particle size and shape. And towards the end, I'll try to show you some molecular materials which can act as rotors, etc. So briefly, what is a microemulsion? If you have two liquids which are immiscible, then you can make them miscible by mechanical energy or by chemical energy. By chemical energy you mean some reagent you add which changes the interfacial tension between the two liquids. So that makes the two liquids miscible. Although they are miscible, there will be aggregates of this surfactant molecule, which is a long chain molecule. It's a hydrocarbon chain with a polar head group, and this is not visible to the naked eye. So these are called transparent emulsion. It's thermodynamically stable, but you can look at them through other techniques like neutron scattering, light scattering, small angle X-ray scattering, or you can look at them through what is called cryo-TEM, that means low temperature transmission electron microscope. So basically you form small aggregates which have dimensions of nanometer size. So you have to control this molecule such that it results in these aggregates which has dimensions of nanometer size. Why you want them in nanometer size is you want to do your reaction within these aggregates. By that you control the size of the particle which you are trying to synthesize in this solution. So if you control the dimensions of this, which has water inside, aqueous medium, you can make particles of this dimension. Okay. So there are some parameters like what is the concentration of water, what is the concentration of the non-aqueous solvent, and what is the concentration of the surfactant molecule which you are using. Depending on that, you will get various aggregates. One is called a reverse micelle, where the heads are inside. If the tails are inside, it's called a micelle. If the tails are inside, the tails are hydrophobic in nature, so it attracts oil or non-aqueous medium. Okay, so then you will get a different kind of structure. You can generate a reverse micelle. This is called a micelle. You can get lamellar phases. You can get cylindrical micelles. You can get vesicles and bicon. There are different types of structures you can generate within the solution, and then you can synthesize. For example, you want a very 2D type of structure, very thin 2D type of structure which is say 1 or 2 nanometer in dimension, but is very large area, then you can generate this kind of structures. If you want spherical particles, then you try to make aggregates like this. Okay. Many of these are biologically relevant. These are present in our bodies, and so this chemistry can be extended to the biology of our system. These are some of the molecules which are called surfactants, which are used to make these aggregates. Some of them have an anionic head, some of them have a cationic head. You can have neutral head, so these are called neutral surfactants. You can have biological surfactants, that means things which are friendly to the human body, they are called biosurfactants. So many of these are actually present in our body, phospholipids, etc. So you can choose your surfactants depending on the application. So there are certain parameters, when you choose a surfactant, you have to know the area of the head group and the volume of this micelle, which will depend on the length of the hydrophobic tail, and depend on this factor, which is called the surfactant packing parameter. You can generalize that you will get a shape of this kind. So you have to choose these numbers to which will give you the type of aggregate that you need in which you want to do your material synthesis. Okay? So there are some more details of, if you want, I can discuss later. So once you have an aggregate, how do you know that you have an aggregate? When you have an aggregate, you reach what is called a critical micellar concentration. At that point, the properties of the solution changes drastically, and you can follow that change using many different physical methods. You can study the osmotic pressure, you can study the turbidity or surface tension, viscosity or self-diffusion coefficients, which will tell you that micelle has formed. Once you want to work with the micelles, it may be possible that you are not getting the right concentration, so you are in a different part of the phase diagram, because you have three different reagents. You have a ternary phase diagram, and you have to understand which portion of that will give you the reverse micelle. Okay? So what you do is you work with different systems, and you generate a phase diagram and map out which part of the phase diagram actually gives rise to what kind of structure. Okay, so once you know that, then you work with that composition. So this is an example, this is a very recent example of a very unusual surfactant we designed. So you can see from a critical micellar concentration of 1, we can raise it to 100. What it basically means is you can enlarge your size of the surfactant aggregate 100-fold by just choosing a type of surfactant. So this is just basic physical chemistry, where you work out the parameters to find out how to increase the water content. So once you know that you have micelles, then what you do is you have to take the component. Say you want to make cadmium sulfide quantum dots. So you take a solution having cadmium and a solution having sulfide ions in the right microemulsion proportion, which I mentioned, like you have to know the surfactant, solvent, etc. And then you mix them. This is a schematic diagram to show when you mix two solutions which have reverse micelles, then they collide and they coalesce in very fast. So it's like in nanoseconds, and some of them are very fast, so they are in picoseconds. But you can, with today's technology, you can follow these processes, and you can find out how many are actually coalescing together, whether 2 or 4 or 3. So you can study, because with femtosecond spectroscopy, etc., you can study these processes very easily today. And what happens when these two mix? Obviously, you will have precipitation, but the precipitation will be controlled within the surfactant aggregate. So the size of the particle will be restrained. So these are more details. Some of these kinetics, how the first step, second step. This is an old slide, but more details have been worked out in the last 20. This is one of the first mechanisms which was proposed for what is happening when two reverse micelles encounter themselves. So you can, by knowing this mechanism, you can alter this equilibrium by adding something. So if you want to make this process more slow, you have to do something here. So if you want it to grow larger, you have to do something here, etc. So these rates and all have been worked out. So we worked on a variety of materials over the last 7-8 years. We have worked on ferroelectrics, we have worked on some magnetic materials, we have worked on GMR or giant magnetoresistance materials. We are working on metastable alloys which cannot be prepared in the bulk. You can make it in the nano dimensions like manganese, nickel, etc. And we have worked on some borides for field emission studies and coatings, etc. So, a large number of materials we have worked on. I will give you one or few examples of the factors which affect the synthesis. So, you can choose surfactant, solvent, amount of water content, the nature of ligand. There are many factors which control the size and shape of the particles. So, what I will show you one example is how to control the aspect ratio of rods. So, you are trying to make nanorods of some metal carboxylate, which if you decompose properly, you will get metal oxide rods, and metal oxides are of lot of importance. So, I will show you how you can control the aspect ratio and shape. We have also worked on a lot of other things. If I have time, I will show you some of these methods. So, the motivation to make the carboxylate nanorods was that it is a precursor to metal oxide nanorods and nanoparticles. Then those particles can be functionalized with biomolecules, they can be interconnected, and can we make large area nanostructures using that. So, that is the ultimate goal. So, this is an example to show that if you use microemulsions, then you get this rod like structure. If you do not use microemulsions, if you just pour the two solutions without the surfactant and the surfactant aggregate is not present, then you will result in minor particles and you will not get this anisotropic structure. Now, this is to show that with the same rod, this is a case of manganese oxalate. Manganese oxides are important because they are used as battery materials. So, that was the idea. I am not showing any property in this talk, but all of them have been characterized using the magnetization, etc. What it shows is that if you use this rod, you can get particles of all the different oxides which are known from the same rod under different conditions. So, for example, if you heat it in air, you may get this oxide. If you heat it in nitrogen, you may get. So, depending on the conditions, you can get all the three oxides of manganese using the same rod. And of course, later if I will show you from the rod, you can also get a rod of the oxide if you control your decomposition. Okay. So, the mechanism why if you use microemulsion you get anisotropic structures is basically this is a mechanism we have proposed, that when this particle forms, you have oxide ions on the surface. These oxide ions attract the positively charged head group of the surfactant molecule, and the ends are hydrophilic in nature, that means they are water rich, and so the synthesis is allowed in this dimension. So, what you are doing, you are restricting the growth of the particle along one direction. So, that is why you get rods only when you use cationic surfactant. If you change to anionic surfactant, then you do not get the anisotropic rods. Now, this is what I was showing, that instead of particles, you can have an alignment of particles. So, if you decompose the rods properly, you can align the particles of the oxides. Instead of getting separate particles, you can control the alignment of the particles. And these dendritic structures can be generated depending on your conditions of synthesis. Now, if you control the solvent, if you change the solvent, you can change the aspect ratio of the rods, the length versus the width. So, we have explained that how you are going from a solvent which is hexane to cyclohexane to iso. These are different organic materials, and the difference is in the hydrocarbon chain. So, if you go from bulky hydrocarbons to less bulky hydrocarbons, then the surfactant aggregates which form an interface between the water inside and the solvent outside gets affected, and the dynamics of intermicellar interaction gets affected, and hence the aspect ratio can be varied using the solvent. So this is another example that if you change the solvent, you can change the morphology from more fibrous type of morphologies. Here the surfactant is cyclohexane, here the surfactant is normal hexane. Now if you change the surfactant, that was solvent, if you change the surfactant, which is a cationic surfactant or a neutral surfactant, you can change the same material from a rod to a sphere to a cube, and if you decompose them, of course you will get nickel oxide. Again, it is an important magnetic material of different particle sizes. But the important thing is that these shapes are dramatically affected by the difference in the surfactants. This is another example to show you how the shapes are changing. So from anisotropic structures, in this case it is becoming nearly spherical by changing the surfactants. So we have given a mechanism why this should happen. If you are changing the surfactants, why this anisotropic growth gets altered from a rod to a cube, etc. This is another chemical we add, which is called a co-surfactant, which also affects the anisotropy. So you can get from rods to cubes by controlling the co-surfactant. So we have explained that as the carbon chain length increases, the intermicellar exchange rate increases and the size increases till a certain level. Beyond certain length of the carbon chain, they start interacting with the surfactant, and again the size reduces. So this is kind of a repetition of that. Now if you change the amount of water content, that is how much water is inside those spheres, you can enhance the size of the particles, which is of course a trivial, it's expected that if you increase the size of the water, amount of water, W naught shows you the amount of water, it's a ratio of amount of water to surfactant, and if that changes, you can increase the size of the particles from 35 nanometers to 130 nanometers. Now we can also change the amount of the nature of the material from very crystalline to amorphous material. So very crystalline materials, if you look under the electron microscope, will show very ordered arrays of the cluster of atoms. So in the high resolution transmission electron microscope, you can see these very ordered structures, and this is called the fast Fourier transform or the electron diffraction. This is in the reciprocal space, this is the real image, and that shows these fine spots, and that is an indication of a very highly crystalline nanorod. Now we can change this highly crystalline rod to an amorphous rod. If you look at this region at much higher resolution, then you can see these particles have become randomly oriented. So we can control the crystallinity of these rods, and when you change the crystallinity of the rods, obviously all its properties will change. The conductivity will change, its optical properties will change, and everything will change. So we have done all those property measurements, but today I am not going to show all those measurements. This is to show that even at room temperature, that was at a slightly higher temperature, even at room temperature we can control the amorphicity of these materials by using a surfactant, but without using the solvent. Let me come to some other materials that we work on, basically for gas sensing and photovoltaic materials. Titania is a very important material, silica is a very important material, and I will show you some examples of metals and alloys. So this is some silica particles that we made by our microemulsion method, and you can see this is very uniform, and this is what is supplied by the world's best company of nanosilica. If you buy, is a transmission electron microscope of the world's best chemical company in these areas. Ours are much more uniform. why we wanted to make silica is biocompatible. So you can use it for, many people want to use it for drug delivery, etc. So with this silica, we attach amino acids. So I don't know, the battery is going down. So I can't, I don't know. You have another pointer or something? So we have amino acids covering silica, and then we made rods as I showed earlier. So this work was, can we put amino acids, biomolecules? So this silica has now been covered with amino acids, and then our aim is to put these amino acids silica particle on the nanorod, and then can we connect the nanorods, so make a large area surface. So we have been able to, this is partially successful, we have been able to connect them, but we have not got very high uniformity. As you see that some of the places it is attaching, but we have to still optimize such that the attachment of the biomolecule surface on the rods is very uniform. Now, for gas entrapment, for example, hydrogen storage and carbon dioxide storage is a very important problem. So we make silica particles with a lot of pores inside, and we can make particles with surface area of 120 to 550 meter square, which is quite high. We are trying to reach 1000 meter square per gram. So if the surface area is very high and you control the pore size, so these porosity is around 5 nanometers here, that we can change to something like 40 nanometers by controlling our reactions conditions, and we have further enhanced it to I think 60 nanometers now, and we can also vary the shell thickness. So we have now a large library of particles with different pore sizes which can trap molecules of interest. So we have been able to trap carbon dioxide and hydrogen, and we are trying to increase the concentration. This is another important material used for a lot of applications, calcium carbonate. It has 3 structures. The most common room temperature structure is called calcite. This is a high pressure form, and this is a form which is normally made by bioorganisms. So if you look at sea shells or things which are in the sea, marine animals, their shell is covered by calcium carbonate, which has a structure of vaterite. It's difficult to make at room temperature in the laboratory. So by our methodology, we could make both these in the laboratory at room temperature at normal pressure. So this is an example that we vary the temperature. At certain temperature you get 74% of this, 26%, and at 40 degrees we get 100% pure vaterite if you use microemulsions, that is the surfactant based method. And these are the structures. These rods are typical of aragonite, the high pressure phase. This is a mixture of vaterite and calcite, and this was in 2007. Now in 2009 we have improved it, and we have got pure vaterite phase. This is an X-ray diffractometer which says that this is a pure vaterite phase at room temperature. By controlling the concentration of reagents and by controlling the rate of the intermicellar exchange, you can optimize from the calcite compound, here you have mixture of vaterite, calcite, and then you get pure vaterite. So this is room temperature synthesis of something which bioorganisms can make, but it is not normally thermodynamically stable at room temperature. These are different structures of vaterite and calcite, and this is normally looks hexagonal. If you look at one particle, it looks like a hexagon. If you look at a low resolution, at high resolution they actually are made up of spheres which for some reason the details of the forces which make them assemble in a hexagonal form are not yet understood, but it tries to assemble in a hexagonal form. Okay? And this is the normal form of the vaterite phase. But we can also synthesize it by controlling our chemistry in rod shape. And this is the first report of a rod-like vaterite form. It has some implications in some applications. Okay. Now let me tell you something about metals and alloys, because metals are of course the most important for any interconnect and all. You want metallic nanowires or metallic particles, assembly of metal particles, alloys. So this is another, the same procedure of reverse micelles, and we are trying to make metals of copper, cobalt, etc. So this is pure copper metals made in 3 different sizes. By controlling the reaction conditions, you can get cubes, rods, spheres. So these are the cubes. This is a low resolution picture of, so says 50 nanometers, but if you look closely, then they are made up of particles of around 5 to 7 nanometers. Okay. Then if you change the chemistry, you can get these kind of wires of copper, and they are very thin wires, around 2 nanometers in thickness, but long wires, and you can control the length of the wire as well. You can, if you change the concentration, you can also get spherical particles. This is something to show about copper is a very good electrocatalyst. So depending on the shape of the particle, its electrocatalysis property changes. So what we show is that the cube-shaped particles are the best, the blue one, and these electrocatalysts are used to evolve hydrogen and oxygen. So this is a very important industrial process where we want to generate hydrogen. So hydrogen evolution reaction. So if you look at the black curve, it is very high, and that is for the cube-shaped copper. All of them are copper particles, but the cube-shaped particles show much enhanced activity. So you put it in water, so hydrogen will evolve at one electrode, and oxygen will evolve at the other electrode. And both hydrogen and oxygen evolution is the maximum for the cube-shaped particles. That means morphology plays a very important role in the electrocatalysis of water. This is to show that this is cobalt particles. The earlier one was copper particles. Cobalt normally stabilizes in the face-centered cubic structure, but we can stabilize it using our methodology in the metastable hexagonal phase at 500 degrees centigrade. So this methodology allows you to stabilize metastable phases, which are normally thermodynamically not stable at room temperature. We can make alloys. We have made alloys of copper, nickel, cobalt, nickel, etc. for various applications, and whole solid solution range we can make, all the up till 100%, and you can get 7 to 20 nanometer particles. This is some more details of depth profile XPS data, which shows you in one particle how does the composition vary. So this tells you that at the center the composition is 1:1 nearly, but towards the surface the copper is higher in concentration. So in each particle you can study the variation in the concentration as a matter of depth. In this case it is more or less constant. So copper is 3 times and nickel is 1 throughout the particle. Similarly, you can study copper cobalt alloys. You can make alloys which look like this, like a core and a shell, or you can make alloys like this, which are actually composites of copper and cobalt, and that you can easily find out using X-rays. If you have 1 peak, it is an alloy. If you have 2 peaks, that means you have 2 different metals. And the shape, so you see this is like a region of more density, of slightly more dense, richer in cobalt, or this is slightly lower in cobalt. So you can map these things. This is iron cobalt, very uniform particles. You can make spheres, you can make wires. Some of the wires, of course, we choose the nice pictures. They show the Y junction. Important for people who want to do electronics, Y junctions are supposed to be very important. This is to show you that we can really control the iron cobalt ratio. So the ratios are as we loaded, iron is 3 or more than cobalt, and here it is 2:1, here it is 1:2, etc. Then we are interested in nanostructures which have two functionalities. Say you have a magnetic core with an optical surface, or you have a magnetic core with a diamagnetic surface. So here we are showing you how to make nickel oxide, which is a magnetic material, which is covered with silica, which is a diamagnetic, which is non-magnetic material. So you first make these particles using the nanorods, and on that you have to coat silica particles. And then we try to control the shell thickness, etc. So if you see a dark region and a light region on top, so that's a core and the shell. So how you study using electron microscopy, you put the beam through the center and you should be seeing both the nickel and the silicon. If you put the beam through the shell, then you don't see the nickel because you see only silicon. So that tells you that the shell is made up of only pure silicon. These are more core shell structures of magnetic materials with silica. Why you want to do is, if you have cobalt oxide has a certain magnetization. If you want a graded magnetic structure, something which has, you want to control the magnetization, then you can coat it with a diamagnetic object. So this is cobalt oxide is magnetic, and you are coated with the silica on top. You can make them spherical, you can make them rectangular, you can make them hexagonal by choosing appropriate conditions. And this is a mechanism we showed that what actually controls the shell thickness, which chemical is important. So we find that the amount of water you add, it is required for a reaction which is called hydrolysis, that really controls the shell thickness in this material. We can take out this core from and make hollow shells. Once you make hollow shells, then you can use it for other purposes. For example, you want to trap some material inside. These are hollow shells. So what we have done is we have trapped some organic reagent, supposed to be a pollutant. So you can use core shell structures for trapping some organic pollutants, etc. Now let me come to some dielectric nanoparticles and nanocomposites. So dielectric nanoparticles are very important because the size of the ceramic capacitors, that depends on the particles which you are using, barium titanate. So as you see that the 1990 limit was 12 micron, we have already achieved something like in 2007 it was 0.8 micron. This is what is predicted in 2014, 50 to 70 nanometers. Okay? And the problem is you have to control not only the barium titanate, which is the basic material, you also have to control the nickel or palladium or silver electrodes which are within the multi-layer capacitor. And if you reduce the size of the particle, what happens, the DC bias, which is very important, that you can reduce when you reduce the size of the particles. So we did a lot of work on trying to make miniaturized these barium titanates and many other ferroelectric and other materials. So these are the reasons what you want. You want to reduce the palladium content in these interconnects. You want to reduce the size of the alloys and the electrodes, etc. This is all very known. So ultimately, you want to have particles with nanograins. So this lot of work we did in 2004, 5, 6 on using this microemulsion method for making a generalized procedure for any dielectric oxide. You can make all the dielectric oxides which are very well known in the literature, like barium titanate, strontium titanate, lead titanate, PZT, PLZT, all those things we can make using this. You have to modify a little bit this initial reagent if you want to make strontium, or you want to make a zirconium compound, then you have to modify. So this is a general procedure which we established over some time. And now you need 3 microemulsions. Earlier we were using 2 because now the number of components has enhanced. You have barium, titanium, and you need oxygen. So you have now 3 microemulsions, and the process is similar. And this was one of the early works we did, and we showed that at 20 nanometer dimension also, you can see ferroelectricity. Normally, ferroelectricity decreases as the particle size decreases. So you lose the ordered moment, but and there are a lot of theories at what size it should disappear. So we showed that at 20 nanometers also we can see ferroelectricity. Of course, the dielectric constant goes down dramatically. Bulk barium titanate has a value of 1500 or something like that. So that value decreases, but the loss also decreases. So you have to trade off the dielectric constant for the loss. We made many other materials which are of use, tantalates, niobates, etc. One thing we did was we tried to enhance the properties of a micron-sized, normally used barium titanate using some nano-sized grains. And because the nano-sized grains will have a lower melting point, it would fuse the micron-sized grain. This was the model. So we made what we call N-mu composites, nano-micron composites, and we were successful. And the morphology suggests very good sintering if you add 1% of nano barium titanate to the bulk barium titanate. And the dielectric constant also gets enhanced at certain very low amount of dosage of nano barium titanate. And the theory is not still clear why at certain compositions it is happening. We have a model based on the ordered moments and how the bulk particle is fusing with the nanoparticle, and we could see in the transmission microscopy clusters of bulk particles and the nanoparticles, and some kind of model we were proposed, but still it is not perfect. Then we made something for some industries, semiconductor inks for coatings and some nanostructured metal borides. This is the smallest particles we have made. These particles are around 1.8 nanometers. Using a special solution, highly stable colloidal solution, so you can spray it over large areas, and you get, this is cadmium sulfide quantum dots, 1.8 to 2 nanometers, very uniform particles. Using the same methodology, but you have to tune your surfactant. So this is a surfactant you will not get in the market, you have to make yourself. This is another example for lanthanum boride is a field emitter. So it's we made nanorods of LaB6, we have made several other borides, niobium boride, etc., which is a superconductor at 8 Kelvin. I will not go into details, but these are all. So what I want to say is, for this part, that this technique is very versatile, and you can get very precise morphologies and uniform morphologies which are low temperatures. You can stabilize phases which are otherwise thermodynamically unstable. You don't need too much equipment. On the negative side, the yield is sometimes low and it may be expensive. So it depends on the applications what you want. Okay. Let me just come to last few slides of what chemists are doing. This is the standard Moore's law. So how do you miniaturize these other than the way I told you particles. People are trying to do what are called molecular electronics, so I have some examples. So why you want to go from microelectronics to nanoelectronics? Of course you want, these are the positive factors. The negative factors is of course very high cost, etc. So some molecular electronics people have been trying, and of course the best molecular machines are in our body, and as you know there are many proteins which act as motor proteins like myosin, etc. And the chemistry of this is very interesting, which is giving us ideas how to make machines in the laboratory. So based on that, people have made molecular rotors, motors, etc. So this is an example. It's not easy actually. This is quite a tricky chemistry. Okay, it works in 5 steps. And so you have a molecule, looks very complex, but what it does is, you see it goes from here to there, and it comes here. So basically it is moving, but it is moving through some chemical processes, these steps. So why does it move? Because of certain interactions and certain strain in the cyclic rings. So the chemistry is not easy, but the idea is clear that you can make such molecular motors. This is another mechanism using light. This is light driven. So you have a light at 280 nanometer. This molecule flips itself. Okay? Then you change the temperature, it again goes to another position. And then again you use UV radiation, this in the ultraviolet, it again flips back. So this is a rotary molecular motor which is activated by light. This is another example of a molecule. Basically under UV light, this bond, there is no bond here, but it forms a new bond. And there is a bond here, this is a double bond that will break. So this can go on continuously. You shine UV light, it goes into this form. You shine visible light, it goes into this form. So this kind of a cyclic thing, processes based on light has been developed by many people, which can be used as a molecular switch. So photochromic molecular switch. The molecular shuttles have been designed, that is molecules which are moving from one part to the other, and maybe I have an example in the next. This is an example of such kind of molecules which move. They are basically bicyclic rings. You will see one ring in the blue color, this is another ring, and this will move through this. One will move up and down the other. This is another case of one ring and this another ring. So one ring holds a photo switchable. This moiety is light sensitive. So once you put in light, then it transforms itself to the transform. The transform can rotate. The cis form cannot rotate. So with light, you can convert this from trans to cis. So it will either rotate or stop depending on the light. So the switchable molecule, this is called a catenine molecule. So there are many examples like that. This is a molecular sensor, I won't go into that. These kind of molecular tweezers have been made. So this is a molecule in which another molecule can get entrapped. This is a fullerene molecule which can get entrapped in another molecule. So these are carbon nanotubes which has been made long back by IBM. This I don't want to say. These are nanowires on which antibodies have been placed, and these antibodies can be used for detecting viruses. The conductivity of the wire changes when the antibody is present. There is some conductance, and when the virus attaches, the conductance changes. So it is kind of a biosensor which is used making silicon nanowires. Field effect transistors have been made way back in 2004. This is another example of silicon nanowire being used to detect proteins and DNA. So, but what you have to do is on the nanowire, you have to put some molecule which recognizes the molecule you want to detect. So this is a process called biorecognition. So you have a silicon fiber nanowire. On that you put a molecule which will detect the virus which you want to detect. So it will latch on to that virus. And when that latches on, some property should change. It should be either conductivity or its photoluminescence or something like that should change. These are nanowires which have been already made. This is silicon nanowires, very long nanowires, which is made by vapor liquid solid growth. This is a technique developed by James Heath at, I think, UCLA. This is a very famous technique now. You can make very standard wires. These are platinum wires of 20 nanometers, and they have made devices out of that. These are very large 40 platinum nanowires. And this is a device which they made, and it's a memory circuit using silicon nanowires and then some organic, very complex thing. There are silicon nanowires, there are metal nanowires like platinum or something, and there is an organic molecule within that. And it functions like this. So you have a platinum wire on top, silicon wire in below, in between you have an organic molecule, and there is an electron transfer. So, and when there is an electron transfer, there is a rotation of the molecule. So it is not a very easy chemistry, it's a quite complex chemistry which is going on. And to make it really viable economically, I think still is a challenge. These are two nanowires which are being joined by DNA. This has been done at Penn State by Tom Maluk some time back. But again, making large area interconnects is still a challenge. It is a stacking of nanowires, formation of nano heterostructures. I think I will not go into that anymore. This is probably the last slide I want to show. You can make nanowires within the microemulsions which I discussed earlier, and you can make Y junctions. One example of Y junctions I told you, you can make like that using microemulsions or surfactant based synthesis. So thank you very much. This is my group.